of values as to where they ended up on this plate. What actually happens, subject to the accuracies of the experiment, is that we don't get a continuous smear of values, we get essentially two values, spin up or spin down in a given direction. And this is one aspect of quantization. From apparently continuous data, you get discrete results. And then that's the single qubit model, already non-classical, but actually technically classically simulable. But once we go to compound systems, then we really get to the point where quantum resources exceed classical ones. And then we get these non-local correlations, as in Einstein's spooking action at a distance. So here is an example of such a state. So you can think of it as either spin up in a given direction or spin down, a superposition of those two things for two particles. So according to the usual story, if Alice were to measure, so we think of Alice holding one half of the entangled pair at her side and Bob holding his half at his side. If Alice measures, and they may be far apart, if Alice measures, then she may get this result or this result, but if she gets this result, then if Bob subsequently measures, he is bound to get that same result. Of course, you can find Bob. So that's people have done experiments to show these extensive experiments to show these kind of correlations. Some of them are quite nice things where they use these observatories in nice Caribbean islands and so on, where they actually turn the telescopes down and beam photons at each other and this kind of thing. But in one way or another, this and then the things it supports, like heat distribution and so on, teleportation, have been extensively demonstrated. What we get from that is that we can actually build quantum realizations, which in turn translate into things that can be produced using suitable physical setups, quantum optics and so on. We can build physical realizations of exactly these kind of situations. So we have to conclude that this is really how the world is, and the world cannot be explained in classical terms by classical sources. Okay, so how am I doing for time? So we're going quite slowly, I think.
Fine, actually.
I'm fine.
Started about 5-10 minutes late.
Okay. All right.
Another 15-20 minutes.
Great. I think I'll be fine. Thank you. So what I'd like to do is I think it's good to look at these examples, and what I want to do is actually look at them now in a very visual way, which hopefully is an effective way of seeing the sort of things we're talking about, in particular this idea of local information and whether or not you can put it together globally. So I'm going to take the Hardy table again, but I'm going to draw it in a certain way, what we call a bundle diagram. And this is closely related to topological ideas about bundles. You can ignore that remark if it isn't helpful. So we've got our variables. So this is very much like that sort of the picture with the sort of ever-ascending staircase that we started off with. So we have our variables, and we think of this as a sort of base space of the variables we're going to measure, and we draw an edge for any two variables that can be measured together. And you see the rows of the table correspond to the edges in this little graph. Okay. These are the co-measurable variables. So A and A prime cannot be measured together. There's like a choice. You either measure in that direction or that direction. You look at this register or that register. This is the incompatibility, which is of measurements, which is in general a feature of quantum mechanics. But those that can be measured together have edges between them like this. Now, above each variable, we have a fiber which gives the possible values that variable can take. In our very simple setting, it's just 0 and 1. It's the same fiber for each variable. And now we draw edges in between these fibers corresponding to the possible joint outcomes. So for the variables A and B, you see we get a full row of ticks in the table. So all possible combinations, all possible combinations of values are possible according to this model, and so we get all those edges. When we go to the other, for example, B and A prime, that's the third row here, there's only 3 possibilities, because we had one of the possibilities being precluded. That was like the 0 that we had in the table. And similarly, for A and B prime and A prime and B prime. So we get 3 edges in each of those cases. So this is a faithful way of representing the model, but it now makes this kind of structure, some elements of the structure, much more apparent. And if you think about it, piecing together, the sort of way we sort of started with that little assignment of values to some of the variables and then trying to extend it, will correspond here to starting with an edge and extending it to a path that goes around. And what we can ask for is there, and in fact, getting a path that goes all the way around and meets itself at the starting point would correspond to a consistent assignment of values to all the variables that satisfies all the constraints. This is what topologists would call a global section. If you have a local section, can be extended to a global one. So let's see if we can do that. Well, firstly, we see that in this table there is some path like that. I've just shown it in red. That is an assignment to all the variables, which is consistent with all the constraints, because it only uses edges that were in the model. So you see it sets A to 1, B to 1, A prime to 0, and B prime to 0. That meets all the constraints and it's consistent. So there is some way of assigning values to all the variables that's consistent with the constraints. However, suppose we take the problematic edge, the problematic entry, this one here, that was involved in our previous argument. The question now becomes, can we extend it to one of these nice paths that meets itself and consistently assigns a value to every variable? And you can see that we now have a problem. Yes, we can extend it, and we can extend it again, and then we can extend it again, but we haven't come back to where we started from. We get a contradiction. Okay? So we're seeing the argument that we sort of gave verbally before. And by the way, I mean, there's a little technical aside, the fact that we can always extend the path somehow, locally, which is like saying that the adjacent boundaries of the Escher building were kind of consistent, is actually the direct reflection in this setting of what's known as the no-signaling principle, which is an important, taken as a fundamental principle, which is satisfied by quantum mechanics and in some sense underwrites its consistency with relativity theory, the fact that it's kind of causally consistent, even though it's not local. If you think about it, that's because we're saying, I mean, to say that you can always extend from a given path is to say, well, you've got to a certain place. So the fact that you had the edge here and it's giving you a possibility over there and then it overlaps with something else, there has to be something involving the other variable that will have the same possibility, which is like saying it has the same marginal in probabilistic terms. And if that meant nothing to you, then we don't need it for the remainder. So anyway, the important point here is that we can extend the path locally, but not satisfy this global condition of coming back to where we're starting, making what we might call a univocal path, which sets a unique value to each variable. And there's just no way of doing that in this thing. And that is exactly a topological way of seeing the contextuality of this model. And indeed, we can make another attempt. So we could start from the other end of that edge and propagate in this fashion, and again, we won't get back to where we started. And there's just you can easily see that that's how it is in this case. So now I want to make the point. So we saw that in a sense the Hardy construction gave us a stronger form of contextuality than what we saw with that probabilistic argument with the Bell table that we started off with, because we didn't need to know the probabilities. But in fact, we can have an even stronger version of contextuality, what we call, in fact, strong contextuality. I'm going to exemplify with a very famous example from the quantum information literature, what's known as the Popescu-Rorley box. Here, the correlations are so strong that they exceed what can be realized in quantum mechanics. So the PR box is not quantum mechanics. In a sense, it's science fiction, but there's a real, one of the major questions in current research in quantum information and foundations is to understand why nature selects quantum mechanics and not these stronger things that are apparently possible, these super quantum correlations. And a lot of the current understanding of quantum computation, quantum protocols, is couched in the general setting of no signaling theories. Now, an interesting point about this table is that it exactly corresponds to the events we picked out in our original analysis of the Bell table. The correlated events on the first 3 rows and the anti-correlated events on the 4th row. But here we put all the weight on those things and zeros everywhere else. It was only up to probability that we could work with those with the original Bell table. Anyway, suppose we write a diagram corresponding to this, a bundle diagram. It's immediately obvious to the eye, when we look at this, that there is no univocal path. Anywhere you start off, you're not going to end up where you started. There's this twist. It's actually, you can see, it's like a discrete version of a Möbius strip. And so we can put them side by side. This is this intermediate form, what we call logical contextuality, exemplified by the Harding model, and this stronger form of contextuality where there's no univocal path at all, exemplified by the PR box. By the way, you might say, is this strong contextuality too strong for quantum mechanics? Well, the PR box is too strong for quantum mechanics, but as soon as you go to 3 parties, then you do have quantum examples. It does arise really in quantum physics as well, that you have this strong contextuality. The famous examples are those given by the GHZ states, Greenberg or Zeilinger states, but you need at least 3 parties to make that work in quantum mechanics. So let's briefly think about how this relates to logic. So people have been talking about logical paradoxes for a very long time, Cretans and other examples of logical paradoxes. So probably the most, well, I mean, Cretan, the most famous one of all is the liar paradox, which is, so the classic liar sentence is the sentence that says that it itself is false. And in the literature, people study liar cycles. So a chain of sentences where each one says that the next one is true, and the final one says that the first one is false. Now, I'm hoping that that kind of is chiming in with what we've just been seeing. Actually, you could model it as a little family of equations, Boolean equations like this. And the point is that although any n-1 of these equations is satisfiable, the whole set of n equations isn't. Remember our general theme of local consistency but global inconsistency. Now, we can think of these as sort of, I mean, if you think of each of the equations, the point is that that induces a certain notion of local information because the various equations, the various assertions only involve some of the sentences. So locally, you can make a consistent picture of what's going on. Now, the observation is simply that the liar cycle of length 4 corresponds exactly to the PR box that we were just looking at. And the usual reasoning to derive a contradiction from the liar cycle corresponds precisely to the attempt to find a univocal path in the bundle diagram. So if you think about the usual sort of way you reason with a liar paradox, I mean, suppose the first liar sentence is true, then by propagating the constraints, that means the next one is, going back to this thing here, then, then the next one must be true, and the next one must be true, and so on. But eventually, when we loop back, we find that we don't get back to where we started, and we've set the value of the variable we started off with to the opposite value. So that gives us, that closes off the first branch of our reasoning, then we try and set it to false and derive exactly the same conclusion. And these 2 chains of reasoning correspond to the first half and the second half of this path that wraps around twice and never gets back to consistently to where it started. And this actually chimes in with sort of current ways of looking at the logical paradoxes. Okay, well, if I still have 5 minutes or so, then let me relate now to something that you might think was very safely far away and secure from all these exotic considerations, namely database theory. Now, the database is a classic topic in computer science. Whether interested in them or not, I mean, our salaries are paid out of them and our medical records are in them, so they're quite prevalent in our world. So we might think they have absolutely nothing to do with what we've been talking about. but actually they provide another isomorphic copy for the kind of considerations that we have been talking about. I think this is worth pointing out. So this is relational databases. So we have a bunch of tables. A database is a bunch of tables. Each table has a number of columns, which are sort of like has attributes. So you have like a bank table, so branch name, account number, and so on. And then the table is populated by a set of tuples, which assign values to each of those attributes. Okay, so this is the standard. This is an early example of scientific operation or something that I think so can't see. Okay, so there's a simple transformation which takes the possibility tables that we were talking about into relational databases. So we think of the things we were calling the variables that we're measuring. We now think of them as the attributes. We think of the outcomes as data values, and we think of joint outcomes of measurements as tuples. And if we do that, then the 4 rows of the Hardy model turn into a little database of 4 tables like this, each with the corresponding attributes, and then with the appropriate filling in the tuples, one for each entry where there's a 1 in the Hardy model. So 4 tuples in the first row and 3 tuples in the first table and 3 tuples in each of the other tables. So that is a perfect, not very, as it stands, not for any application an interesting database, but it is a database, and by extension we can see that there's a correspondence between the usual kind of relational database instances and the kind of tables we've been talking about. Given that, it's natural, sort of unavoidable to ask, what is the database property corresponding to the presence of contextuality in our table? Or did it escape the notice of database theorists? And there were some very sharp people, always been very sharp people working in databases, this kind of phenomenon. And the answer is indeed it did not escape their notice, of course not in this context, not in this, with this interpretation, but as an important structural feature of databases. It certainly did not escape their attention. And it was a very active area of research in the sort of early heroic age of relational database theory, late 70s, early 80s, with people like Beery, Fabian, Vardy, and others, Meyer and others, very actively involved in this. The point at issue was the question of what was called the universal relation assumption. Is there one big table, at least conceptually, up in the sky, from which we can recover all the little tables in our database by projection? And interestingly, and of course the exact isomorphic copy of our previous discussion translated into this language is that for the particular case of the Hardy table, there is no such universal relation. Now, the interesting point is that it was discussed as a kind of discipline for databases, and was considered, and it was rejected because pragmatically this is a global constraint, as we've seen, and it's just too expensive to maintain. So if you think about it, if you took a bunch of tables, you could take their natural join, but in general we know that's going to be a lossy thing, and so you're not going to, when you project back, you're not going to get exactly what you started off with. Now, almost certainly, that in any real database that's out there in the field with our sort of records of interest in it, it will not satisfy the universal relation assumption. So contextuality is alive out there in the world of data. And in fact, there's quite a comprehensive dictionary here, and it goes a bit deeper than considerations we've been looking at. For example, in the world of these kind of probabilistic measurements, coming actually from a quite different motivation, there's some classic work by Vorobyov, giving conditions on the sort of sets of variables, the schemas, under which you can always glue together probability distributions that agree on their overlaps. And this condition turns out to be equivalent to a famous condition in database theory, namely acyclicity of database. So it's a well-studied condition. Okay, and perhaps, yeah, there are other things we can say, but I'll skip over that and I should be winding up. So let me come to this point. Why do such similar structures arise in such apparently different settings? It would be a fair question, given that we've been looking at some of these examples. So I think the clear answer is that the phenomenon of contextuality is pervasive. Once you start looking for it, you can indeed find it everywhere. I think it occurs in a more remarkable form in quantum mechanics. There are ways of constructing it that are using quantum resources in a manner that we've sort of hinted at that are likely to be fruitful and important. But developing the tools to understand contextuality and to work with it may be important in many of these fields. I mean, I did just skip over a natural language example, but I think that is a natural place where some of these tools could be helpful. So if you like the contextual semantics hypothesis, we can find some common structure in all these manifestations and develop the theory. And there's already quite a lot of work that's gone in that direction. And if you want to pick up some further details about what I've been talking about, there's a sort of paper which is aimed at computer scientists, which appeared recently in the bulletin of the EAGCS, the Yuri Gurevich Logic Conference, but it's also available on the archive. I should also mention that I have the pleasure of working with a lot of people on these things. The constraint satisfaction angle with Fokian Velitis and Georg Gottlob, the logical Bell inequalities with Lucian Hardy, the sort of general framework very much with Adam Brandenburger, who's a well-known game theorist, and colleagues from Imperial that I mentioned earlier, which is in natural language. And, well, there are exciting things happening recently. The topology is the connections are quite substantial to the level that one can use these kind of idea of obstructions to gluing local information together, which is very much in the classic language of topology, can be made precise in the language of cohomology, and it can be related to all versus nothing arguments, which play an important role in quantum information. And there are some interesting recent developments connecting this to as a necessary condition for achieving a quantum speedup. And perhaps it's also worth saying another recent result that this sort of stronger form of contextuality that we saw exemplified with the Hardy model is not some kind of rare occurrence, but is essentially everywhere in the sense that given any entangled state, you can find local observables for which you will see this kind of phenomenon. Okay, and there are various papers all available on the archive which have further details of the things that we're talking about. Okay, well, thanks very much.
Thanks. Questions?
So, are these processes that generate relational databases similar to the sources of quantum theory? So when you mentioned the relational databases for which there is no one single table, so
yes.
Does it imply that there are the processes that the source of these relational databases is kind of quantum-like?
No, I wouldn't make that claim. I mean, it's very easy to see that if you have a large database that's being sort of added to in many, in a non-centralized fashion, it's very easy to introduce global inconsistencies, even though locally it looks consistent. The interesting point to me is that from a sort of pragmatic engineering point of view, I guess, or so you could say from complexity considerations, that it was concluded that you couldn't really enforce that constraint of global consistency. I mean, it would kind of imply you'd have to have all updates going through some central thing that would make this global check, and that was kind of prohibitive.
Like a use sum.
I mean, the interesting point maybe is what are the consequences of this, and that's I'm not too clear, but I think it is an interesting question.
Have you looked at weak memory, which is a particular example of distributed systems, and that is something for many of these things? And there's some strange
Right,
conditions.
so it could be where, I mean, you did, so you have, right, so you have, it could well be an interesting example where you have local consistency, you're trying to achieve local consistency.
Yes, and they impose certain global consistencies, which, to my simple brain, I can't see how they help, but they do help a heck of a lot, in the sense you can get proofs with them and not without. So, for example,
Right, so it's sort of like an invariant.
single locations, everybody sees them changing in the same order. And
Yes,
this is a bit of, by engineering genius, they do that, and
Yes.
then the whole system becomes usable.
yes.
So,
But it may well be that I mean, this is what you need to sort of somehow impose the global consistency.
yes.
And yeah, well, I should look at that. Thanks. Yes. I mean, maybe you can tell me that afterwards.
How about local inconsistency or global consistency?
Well, that would be somewhat miraculous. Do you have examples in mind?
Dictatorship.
Sorry.
Dictatorship.
Dictatorship. I see. Interesting. Yes.
I mean, you could imagine something like that, right? Somehow things cooperating and then things getting better or something like that.
It's getting better. Yes. Sort of rescuing yourself from inconsistency.
Yeah.
Well, do you have some particular example?
No.
It would be very interesting if there was such a...
Maybe some fault tolerant things or
Yeah, I
something.
mean, you can imagine some non-monotonic thing
Yeah.
where you sort of need to revise things and go towards, you sort of repair inconsistencies. That's the sort of thing that suggests itself. Yeah.
Would it be natural to express something like the no-cloning theorem in terms of topological constraints on golden diagrams?
No cloning. I've looked at no cloning from a somewhat different point of view. Does something suggest itself to you? I mean, so that's a very specific suggestion, so
I'm
I'm
just
just...
wondering if there are some of these
Yeah.
broader constraints that could be expressed fully in this.
Yes. I mean, it's very interesting because there are inconsistencies between, in quite a general way, between cloning and some of the things that you can do in quantum information. So it's sort of, because you can sort of duality you have in, I mean, sort of the fact that you have some strong kinds of so you have compact closure or, you know, sort of these structures where you have kind of loops and so on. If you try and combine that with cloning, then you get quite a general argument that can't happen unless the whole thing collapses. So that's the sort of abstract perspective on cloning that I'm familiar with. But yeah, it would be interesting to think of a topological perspective on that. I mean, topologically, you do have, you know, if you think about these sort of, you do have sort of codiagonals and this kind of thing. I mean, that means something. The problem is, I mean, the issue is, can you do, I mean, so it becomes quite delicate because what you're really saying is that it's kind of basis dependent and it isn't natural in the appropriate sense. So, but yeah, it would be interesting.
So your probability calculations on these tables is simply having some sort of negative things and amplitudes instead of probabilities. Does that make any difference, or? So sort of, I would have thought maybe sort of going from classical setting to quantum setting, if you had negative entries plus amplitudes as instead of probabilities.
Well, these tables can be realized by quantum things. And quantum things give rise to honest probabilities, as we know. And actually, in a sense, the sort of attempts to reconstruct, recent attempts to reconstruct quantum mechanics start from the probability tables. And they say, you know, how do we get from that to this representation in terms of complex numbers and Hilbert spaces and so on. That's So, and indeed, well, and of course, having amplitudes and the possibility of interference effects and so on,
Yeah.
you can do some of these weird things that you can't do
Yeah.
classically. I mean, there is a result that from this paper up at the top there, other people have made similar observations, but that you can recover, well, in a sense, you can recover the classical source picture if you allow signed measures on the variables, on the hidden variables is what you should be saying. So if it's, in other words, negative probabilities. And the only problem with that is what do the negative probabilities mean? They have been discussed by Feynman and Dirac and other people, but it's not very clear. So we actually, in this paper here, we actually give a sort of operational picture of the negative probabilities. But I wouldn't, I think it's something worth thinking about, and perhaps seeing why nature, it may be easier to see why nature excludes some of these things, because the important thing to remember here is that once you allow these negative probabilities, you can account for all no single theories, and actually exactly the no single models.
But this is related to the fact that in the set of all compound states in quantities is not a simplex, so you cannot represent it as a. So so you can get out you have to get out of a simplex, and that for that you would need exactly negative weights.
Yes, but the no singling world is also a simplex. So the thing, the sort of the picture we're confronted with is that we have the local simplex. I mean, the things that are bounded by the sort of Berlin inequalities and so on. A much larger no signaling simplex, which is actually still pretty complicated on looks of it. And then sitting in between them is quantum set. Which is much more complicated because it's not even a simplex. I'm trying to understand why nature picks out that quantum set as it appears it does. And actually, there are even quite basic questions that aren't understood there fully, such as, for example, is it decidable whether you're in this quantum set? That's quite a subtle point.
Is that intangible witness? Yes.
No, it's sort of saying, if I give you one of these finite tables, I'm asking, can it come from some quantum state? And interestingly, we know we can enumerate all the things that come from a finite dimensional quantum realization. And we can filter out all the things that don't come from an infinite dimensional quantum realization, but we don't know if there's a gap in the middle. And if it's undecidable, it's showing that there are some finite tables which actually require infinite degrees of freedom to be realizable in quantum mechanics, which I would think of as a kind of physical statement. So it's it's an example of the kind of quite subtle questions that open up when one
this conceptuality, is it consistent or can you explain principle of uncertainty?
Uncertainty?
Yes.
Well, so it's obviously related to the, yeah, I mean, yeah, that's a good point. So, I mean, as I kind of we mentioned briefly sort of earlier on, I mean, so what I like to say is that I mean, the interesting examples of contextuality take you to the edge of paradox, or the border of paradox. It doesn't actually cross the border, there's no direct conflict between logic and what we see, but it takes you to the border in the sense that you have these local things that are consistent, but you can't put them together consistently. And what that's telling you is that it can't possibly be the case, not just under the